Nature is complex. Ecosystems are multi-factor relationships between the organisms in the environment. The immense number of factors affecting them makes it challenging to monitor the system. Only looking at a handful of parameters is not enough. That's where nature's complexity can be used to our advantage. Changes in the water quality will immediately affect aquatic organisms. By reading their reactions, we can hack into the ecosystem and monitor the overall condition of their home. Using this relationship, we get a new, fresh insight. Creating robots cooperating with nature. We introduce Robocoenosis.
The groundbreaking idea of Robocoenosis is to use life forms as sensors on a robot that runs over very, very long run times, several weeks or months, autonomously in the environment. Life forms, in comparison to classical sensors like O2 sensors or temperature sensors, generate completely different kinds of data that are far more correlated to the status of the lake. For example, the life forms react much earlier to changes or to biotoxins in the water than a classical sensor would do. Plus, the biohybrid sensors need much less power, which allows us to have much longer runtimes of these biohybrid robots, because we can run robots for weeks or months just on very small amounts of power we can produce with microbial fuel cells directly in the lake in the field of operation.
I think the most groundbreaking thing in this project is the extent to which we go to make the robot completely autonomous and only use the technology to power the robot and to observe. We're not going to take any samples. So this is, to me as a biologist, not taking samples is taking a step away from the lab. This is very foreign to me, sort of hack into the ecosystem without bringing it to the lab. I think the most challenging part is going to be able to confidently read the organism's reactions and draw conclusions, clear conclusions from them. So when you use a sensor, you get a clear result, a number, for example, oxygen level. When it comes to using organisms, we can only tell that they're stressed, but we can't tell what it is that's stressing them. That's why we're using multiple organisms and examining all of the reactions at once. This is going to be the most challenging part, to be able to say they are all stressed by this one thing, and therefore we can start treating it or predicting what's going to happen in the future. We have chosen to work in two lakes representing two completely different environments. The crystal clear water of Lake Millstatt is supplied from the Alps, making it oligotrophic, meaning poor in nutrients. Located in Carinthia, it is around 150 meters deep, and the water temperature goes as low as 3 degrees Celsius. Thanks to our cooperation with Bundesforste, we gained access to many commodities, such as boats and a big research building. These facilities have made the experiments more efficient and robust. Lake Neusiedl in Burgenland represents a completely different environment. The lake is extremely shallow, with the deepest point at less than 2 meters. Lacking any external outflow, the water exchange relies mostly on the rainfalls and evaporation. The vast reed belt along the shoreline in certain parts reaches many kilometers in width. Due to the low water volume, it is especially vulnerable to nutrient intake and temperature rise, making it highly eutrophic, meaning rich in nutrients. Thanks to our cooperation with the biological station in Ilmitz, we gained access to the research facilities, laboratories, boats, and other amenities. This has enabled extensive testing of the prototypes and carrying out various biological experiments. We have chosen various organisms widely recognized as good biosensors. First species of focus is the zebra mussel, Dreissena polymorpha. It is extremely sensitive to low oxygen and responds to such stress immediately by closing its valves. Reading the valve movements, we gain insight on the mussel's well-being. Second species of interest is Daphnia, commonly known as water flea, a small planktonic crustacean. It is known to react well to changing oxygen level, pH, temperature, and other factors. Most immediately noticeable change is their swimming behavior. The stress reaction can present itself in clustering, increased sinking, or swimming in circles. We constructed several prototypes designed to observe life forms. The focus was placed on low power setup and autonomous functioning long term. The robots have a biologist-friendly design and are easy to operate. Early prototypes include various sensors as a calibration method. The first biological experiments rely on visual cues, therefore a camera is included in the setup. The special part about the Robocoenosis entity is its self-actuation. The microbial fuel cells, or MFCs, provide an energy harvesting method that will supply just enough power for the robot. MFCs rely on bacterial activity within the anoxic sediments. Certain parts of the robot are meant to remain in the environment. Therefore, it is essential to ensure their complete biodegradability. To accomplish this, we will be using various environmentally friendly materials such as wood, paper, cotton, and many others. We are developing a recovery system to resurface the non-biodegradable parts of the robot automatically. This way, no artificial parts will be left behind.
I hope that with the project Robocoenosis we can show that it is possible to generate technology, to generate autonomous robots that include life forms as sensors or also as a tool to generate energy that can run for very, very long run times, and that life forms are a can be a new kind of sensor that delivers much better data.
I think very efficient environmental monitoring is where we will go towards. In 20-30 years, suppose we find some organisms that are bioindicators for certain changes in the environment, and we find low power methods to track them. Basically, the entire lake can be filled with sensors.